so
is being recorded.
We can start. Good morning to you, good afternoon, good day, bonjour à vous, buon pomeriggio a tutti voi, guten Morgen, buenos días a ustedes. Welcome to Paris and to the International School of Astrophysics Daniel Chalonge-deVega for this lecture on neutrino oscillations. And we have the great pleasure and the great honor to welcome here today Professor Dr. Takaaki KAJITA from the Institute of Cosmic Radiation Research and University of Tokyo, and a Nobel Prize in Physics. Professor Takaaki KAJITA was born at Saitama in the small and peaceful city of Higashi Matsuyama, and in a peaceful environment, as he used to say, surrounded by rice fields. He studied there at Saitama University and Tokyo University, and received his doctorate in 1983, and already started in a very great avenue and with great people and in a great place. His advisor was a future Nobel laureate in physics, Professor Masatoshi Koshiba, one of the pioneers in neutrino astrophysics, and got the Nobel Prize in 2000, Professor Koshiba, the Nobel Prize in 2002, and shared with Giacconi and Davis, where starting the solar neutrino problem in some sense, formulated. And in 1987, the discovery of the supernova, 1987, named after that, outside the Milky Way with the neutrinos detection in the Magellanic Cloud. In 1998, Professor KAJITA did in Super Kamiokande the great discovery of cosmic neutrinos, and more than that, the fact that the neutrinos oscillators switch in the different types, because they were able to detect different types, because of the interaction between of the cosmic rays and the Earth atmosphere, which, by the way, also showed that neutrinos have a mass, pushing for an extension of the standard model of particle physics. I should add that besides that, and solved the neutrino, so-called solar neutrino problem, and provided an elegant detection set too of the interference between the phases, the quantum mechanical phases of the different type of neutrinos, and so a fundamental property of quantum physics, quantum mechanics. And this, I would like to mention very briefly that for this discovery, he received the Nobel Prize in Physics in 2015, shared with Arthur MacDonald, who, by the way, was here in this same place, also reporting his discovery with the Sudbury Observatory, which was an independent verification, an independent discovery of these important results, which opened an avenue for neutrino physics and astrophysics. And Professor KAJITA is from the 1st October 2020, became the president of the Science Council of Japan, is the director, the PI of the Institute, the modern, I mean, a very active too, Institute for Physics and for the Physics and Mathematics of the Universe in Tokyo. Received many prestigious prizes besides, of course, the Nobel Prize, but before the Bruno Rossi Prize, I would like to mention, Wolfgang Panofsky Prize, and many honoris causa from different universities, which I would like to mention too, because that shows the places, historical places for cosmic rays, neutrinos. I mean, one was from Bolivia, La Paz, as you know, Chacaltaya Cosmic Ray Station. I mean, Shukawa, Mesons, Bruno Rossi was there too. Another honoris causa from Federico II, Naples University, Perugia Università, la Université de Berne. He remains an active physicist in cosmic neutrinos, cosmic rays, neutrino physics, but also with the Kamiokande gravitational wave detector, which is running and have collaboration with LIGO and Virgo for the gravitational waves. That is also a very, very active, actual, and hot topic. And last but not least, I would like to say that Professor Takaaki KAJITA always nicely thanks and do not forget, never have forgotten to thank his collaborator, his advisor, his colleagues, but also, as he liked to say, thanks neutrinos and cosmic rays, who provided him so beautiful discoveries. So is also searching for non-standard interaction between solar neutrinos and quarks. And so along his life, he passed from Kamiokande, Super Kamiokande, Hyper Kamiokande, and I thank you very much, Professor Takaaki KAJITA, and now the floor is yours. Thank you.
Well, okay, thank you very much for the very kind introduction, and thank you very much for the invitation to this seminar. Today, I'm going to talk about Neutrino oscillations. I hope you see my slide.
Yes, very nice.
Yes, thank you. And well, in fact, this is the outline of this talk. First, I'm going to talk about neutrino problems. Then I want to move on to neutrino oscillation studies, nu mu to nu tau, nu e to nu mu, and nu tau, and the third oscillation channel. And then I want to move on to the future prospect. In particular, I want to talk about the CP violation, and I want to summarize this talk. And clearly, well, this talk is kind of a review talk on neutrino oscillation studies. Therefore, I'm afraid I'll have a significant overlap with the Art McDonald's talk 1 year ago, but I hope that is okay. So let's move on. Okay, neutrino problems. Well, the first problem was the solar neutrino problem. As you know, the sun generates energy by nuclear fusion processes, and neutrinos are created by these processes. Therefore, the observation of solar neutrinos is very important to understand the energy generation mechanism in the sun. So the first experiment was carried out more than half a century ago. The first experiment was the Homestake experiment, and this experiment observed solar neutrinos for the first time. However, the observed event rate was only about 1/3 of the prediction. So this was the solar neutrino problem. And in fact, we knew that there are fewer solar neutrinos than expected already more than half a century ago. So this was a big mystery, and therefore people had various additional experiments, observations. And in fact, in the 80s and 90s, several experiments observed solar neutrinos. And here I summarize the results from the gallium experiments, chlorine experiment, and water-Cherenkov experiment. And all of them confirm the deficit of solar neutrinos. So solar neutrino experiments in the 80s and 90s only confirmed the deficit of solar neutrinos. Okay, well, in fact, there was another problem. Another problem came from atmospheric neutrino observations. First of all, I want to say that in 1965, atmospheric neutrinos were observed for the first time by detectors located extremely deep underground. One was in India and one was in South Africa. Anyway, again, more than half a century ago, we knew atmospheric neutrinos exist. Then, in the 1970s, newly proposed grand infinite theories predicted that protons should decay with the lifetime of about 10 to 30 years. Well, this was really a great prediction. So several proton decay experiments began in the early 80s. And here I list the experiments that started the search for proton decays in the 80s. Now, the atmospheric neutrinos have been the most serious background for the proton decay searches. Therefore, these backgrounds should be understood in order to find the proton decay signals. And during these studies, a significant deficit of atmospheric mu-neutrino event was observed. Here, I copied the result from Kamiokande in 1988. In that paper, Kamiokande simply counted the number of mu-neutrino events observed. That was 85, and compared with the Monte Carlo prediction, which was about 140. Also, Kamiokande compared the number of electron-like events, and for these events, the data and Monte Carlo agreed reasonably well. So this kind of observation was reported in this paper. And in that paper, Kamiokande concluded that we are unable to explain the data as a result of systematic detector effects or uncertainties in the atmospheric neutrino fluxes, some as yet unaccounted for physics, such as neutrino oscillations, might explain the data. In fact, later, the IMB experiment, another Water-Cherenkov experiment, also observed similar results. So, atmospheric mu neutrino deficit was with us already in the late 80s. Now, I want to move on to the discovery of neutrino oscillations. The first discovery was nu-mu-2 nu-tau. Now, before moving on, I just want to mention briefly about the motivation to study neutrino oscillations. In the standard model of particle physics, neutrinos are assumed to be massless. However, physicists have been asking, neutrinos really have no mass. Also, it was generally believed that if neutrinos have very small mass, the small neutrino mass may imply physics beyond the standard model. Typically, people discuss seesaw mechanism. And if neutrinos have very small mass, they change their flavor while propagating in the vacuum or in matter, namely neutrino oscillations. So we have good reasons to study neutrino oscillations. And the detector I'm going to talk about is the super Kamiokande detector. It is a 50 kiloton Water-Cherenkov detector. The fiducial mass for the studies of contained neutrino events is 22.5 kilotons. It is located deep underground, 1,000 meters from the top of the mountain. Now, I mentioned there was atmospheric mu neutrino deficit already in the 80s. And well, one of the possible explanations at that time was neutrino oscillations. But well, neutrino oscillation was one of the possible explanations. Therefore, we had to, first of all, we had to find if neutrino oscillations could be the real explanation to the deficit, or maybe some other explanation can really explain the data. So we wanted to separate neutrino oscillations from other possibilities. And for this, we considered this way. These atmospheric neutrinos are created everywhere in the atmosphere of the Earth. Therefore, some of the neutrinos are created above the super Kamiokande detector. And these neutrinos come to the detector after traveling rather short distances, typically, say, 10 kilometers or 20 kilometers. And since the traveling distance is rather short, they may have no time to oscillate. On the other hand, neutrinos are also created in the other side of the Earth. And these neutrinos have to travel long distances. And therefore, they may have enough time to oscillate. If we think this way, we can easily say that we should observe the deficit of upward-going muons. In fact, in Kamiokande, we tried to observe this effect. And in particular, in order to study the up-down asymmetry, you have to use an event with a reasonably good angular resolution. I mean, a reasonably good correlation between the neutrino direction and the lepton direction. And for this, we studied multi-GeV neutrino events. And here I show the data from Kamiokande. And well, cosine theta 1 means downgoing neutrinos and -1 means upward-going neutrinos. And in fact, already the Kamiokande data showed some hint for the upward-going mu neutrino deficit. However, as you can see, the error bars are large, and therefore the statistical significance of the up-down asymmetry was less than 3 sigma effect. So, unfortunately, the data was quite interesting, but the data statistics were not large enough. So it was clear that we needed much larger detector. And that was Super Kamiokande. Now, well, certainly Super Kamiokande is about 20 times larger in the fiducial volume. Therefore, Super Kamiokande can study 20 times more neutrino events than Kamiokande. Well, therefore, Super Kamiokande neutrino statistics are high. However, if the statistics is high, you have to have a fully automated analysis. In fact, one of the limitations of the Kamiokande analysis was the necessity of the event scanning for all data and Monte Carlo events due to no satisfactory ring counting or ring identification software. Well, here I show an event display of Super Kamiokande, and you can identify 2 Cherenkov rings by eye. But during Kamiokande time, we didn't have good enough software to identify 2 Cherenkov rings. Therefore, we had to scan all of these events, not only real events, but also Monte Carlo events. That was a very serious limitation for the high statistics studies. In Super Kamiokande, well, there was a very nice idea. This idea used the Hoff transformation plus maximum likelihood. And with this, we were able to separate a single Cherenkov ring and multi-Cherenkov ring events rather precisely. So with this, we were able to analyze the Super Kamiokande data fully automatically. And I think that was one of the key to the success of Super Kamiokande. And of course, in Super Kamiokande, we have various event categories in atom-sec neutrinos. Lowest energy events lowest energy events are fully contained single ring muon-like and electron-like events whose mean energy is about 1 GeV. Then we have partially contained event where muons, mu interaction occur inside the detector, but the muon exit from the detector. And these events are recognized as partially contained events, and the mean energy is about 10 GeV. And finally, we have the upward-going muons. These are mu interactions below the detector, and only upward-going muons are detected, and the mean energy is about 100 GeV. And all these events are used in the analysis, And in my opinion, the most powerful events were the partially contained events and multi-GeV single-ring muon-like events. And from now on, I'd like to show the Zinsang distribution for these events. Well, maybe you have seen this slide, but anyway, this is the Zinsang distributions for multi-GeV muon-like events plus partially contained events. And for downgoing neutrinos, the data and Monte Carlo agreed quite well. But for upward-going neutrinos, data showed almost a factor of 2 deficit. So, and the statistical significance was more than 5 sigma. And therefore, basically, we were able to convince the neutrino community that neutrinos oscillate. In fact, other data samples also showed a consistent result. So, Super Kamiokande concluded that the observed Zinsang-dependent deficit and the other supporting data gave evidence for neutrino oscillations. Well, of course, I think this was a very important discovery. And well, the importance of the small neutrino mass were well known. Therefore, various atmospheric neutrino and accelerator-based long-baseline neutrino oscillation experiments have been studying neutrino oscillations in detail. And here I list maybe the partial list of the neutrino oscillation experiments that studied nu mu to nu tau. In particular, I just want to review the progress in the understanding of the nu mu to nu tau oscillations based on accelerator experiments. The initial experiment was the K2K experiment. They observed the deficit of muon neutrino events after 250 kilometers. In addition, they observed the hint for the energy-dependent deficit of muon neutrinos. Then the next experiment was MINOS, and MINOS had much higher event statistics. And in fact, the energy-dependent deficit of muon neutrino is much clearly seen. Then the present generation experiments are T2K and NOVA, and these experiments tune the beam energy so that the maximum oscillation effects should be observed. In fact, compared with the no oscillation expectation, the observed muon event rate is very low. So clearly, in the last 20 years or so, the neutrino understanding of the neutrino oscillation had really significant improvement. In addition, if the nu mu deficit is due to nu mu to nu tau, we should be able to observe tau appearance. And this was achieved by the opera experiment. They used the emulsions and they observed the tau decay, kink, and event statistics is more than 5 sigma. In addition, Super Kamiokande and IceCube try to observe nu tau events via statistical analysis, and both experiments observed evidence for tau neutrino appearance. So overall, the data are just consistent with tau appearance. The next topic is neutrino oscillations, nu e to nu mu plus nu tau. I mentioned there was solar neutrino problem. Well, from the early days, people discussed if the deficit was due to the problem in the solar model or problem in neutrinos, namely neutrino oscillations. And a great idea appeared in 1985 by Herb Chen. He proposed to use heavy water to observe charged current interactions and neutral current interactions in the same detector. And this way, of course, charged current interactions only observe electron-neutrino flux, and neutral current interactions observe the total neutrino flux. Therefore, this experiment should be able to tell if the problem is due to solar problem or neutrino oscillations. And this idea was realized in the snow detector. It is a 1 kiloton heavy water detector. And one of the problems is to identify neutral current interactions. The final state is neutrino plus proton plus neutron. Naively, none of these particles emit Cherenkov photons. And therefore, you may consider that it is impossible to observe these neutral current interactions. However, the SNO collaboration had a very good idea to identify the neutrons produced by neutral current interactions. The first idea was to simply use pure D2O, because neutrons are absorbed by deuteron, although the cross-section is very low. After the absorption, 6.25 MeV gamma ray is emitted, and therefore we can observe the Cherenkov photons. The second phase or second idea was to put the 2 tons of salt into heavy water. Then the neutrons are captured by chlorine-35, and the capture cross-section is very large, and therefore you can much improve the detection efficiency of this neutron. And furthermore, the total energy release is 8.6 MeV. Therefore, you are easier to identify these neutron signals. And the final phase is to use the helium-3 counters. Neutrons are absorbed by helium-3. And this way, neutrons are measured in a completely independent way. Neutrons are measured by helium-3 counters, not by Cherenkov radiation. So these were the methods SNO used. And in fact, the SNO experiment was very successful. Here, I show one of the results from the SNO experiment. Here, the horizontal axis shows the constraint on the nu E flux, and the vertical axis shows the constraint on the nu mu plus nu tau flux. Since charged current interactions are only sensitive to the nu E flux, therefore, the constraint shown by red band is really vertical. On the other hand, neutral current constraints from neutral current is shown by the blue band. And furthermore, both SNO and Super K had an neutrino electron scattering, elastic scattering events. And these events are mostly sensitive to the nu E flux, but there are smaller sensitivity to the nu mu plus nu tau flux, Therefore, both SNO and super K had a constraint using the neutrino electron scattering, and the constraints are shown by green. And clearly, these 3 or 4 different measurements intersect at a point, and intersect clearly indicates non-zero mu plus nu tau flux. So this was the evidence that solar nu E oscillate to nu mu plus nu tau. So basically, we understood that solar neutrino problem was due to neutrino oscillations. However, well, there were some people who were not completely convinced that solar neutrino deficit was due to neutrino oscillations. There could be some other mechanism to convert nu E to other neutrino flavors. And in fact, the Kamland experiment played a very important role to convince people that nu E really oscillate. Well, Kamland is a 1 kiloton liquid scintillator detector. And well, when Kamland was operated for the first time, there were several, well, actually many nuclear power stations around Kamland, and many of them were located at a distance of about 180 kilometers. So if we consider this way, Kamland is a very long baseline nuclear, very long baseline neutrino oscillation experiments with nuclear power stations. And the result is, in fact, very convincing well, here I showed the electron neutrino survival probability as a function of L over E. And clearly, the data showed deficit, recovery, and so on. So clearly, this was a very strong evidence that nu E oscillate. Now, I also want to mention the Brexino experiment. Brexino is a sub-MeV solar neutrino experiment. And here is a summary of the Brexino experiment. And in fact, Brexino observed from PP to boron-8 solar neutrinos, and the observed nu E survival probability was just consistent with the MSW prediction. So it is really great to see the Brexino data. The data are consistent with the MSW prediction. And finally, I want to mention that observation of the CNO neutrinos were also achieved in Brexino. I think this is another great achievement in Brexino. Now I want to move on to the neutrino oscillations, the third oscillation channel. Well, in '98, we understood that the atomic neutrino deficit was due to neutrino oscillations. Then in 2001-2, essentially, we were convinced that solar neutrino deficit was due to neutrino oscillations. And since there are 3 neutrino flavors, there should be the third oscillation channel. Then after that, the community's interest was to discover the third oscillation channel. And here I list the experiments that contributed to the discovery of the third oscillation channel. In fact, there are 2 types of experiments. One is the accelerator-based long baseline neutrino oscillation experiments. they try to observe the nu-E appearance in the nu-mu beam. Another is the reactor-based short baseline, typically 1 kilometer to 2 kilometer neutrino oscillation experiments. So they observed the deficit of nu-E's in these short baseline. And indeed, around 2011 and 2012, these experiments observed the effect that were predicted by the third oscillation channel. An accelerator-based experiment observed the nu-E appearance. The reactor-based experiments observed the disappearance of anti-electron neutrinos. So the basic structure for three-flavor oscillations have been understood about 10 years ago. Of course, before going that, I'm going to talk about the present status, but before going to talk about the present status, I just want to summarize the main experiments that contributed to these studies. And you see there are many experiments that contributed to the oscillation studies. Now, if we understand the neutrino oscillations, then it's very important to understand the oscillation parameters. There are three mixing angles, theta 1, 2, theta 2, 3, and theta 1, 3. And there are two delta m squares, delta m 2, 1 square, and delta m 3, 1 square. And here I copied the one of the most updated combined analysis of all these neutrino data. And well, unfortunately, at this moment, we are not completely sure if nu3 is the heaviest or the lightest. People say that if nu3 is heaviest, this is the normal ordering, mass ordering. And if nu3 is the lightest, it is inverted mass ordering. In any case, at present, we are not sure which is correct. So here in this chi-square distributions, both assumptions are the chi-square distributions based on these two assumptions are plotted. And I just want to mention the accuracy of the parameter determination. You see that mixing angles are now determined to an accuracy of 1.5 to 3%. Also, delta m square is determined to an accuracy of 1% to again 3%. So now we understand neutrino oscillation parameters rather well, except for the last one. This is a CP phase. And I'm going to come back to this point later. Anyway, from these studies, we know that neutrino mass is very small, probably more than 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. Also, we know that neutrino mixing angles are large compared with the corresponding quark mixing angles. Okay, I want to move on to the future prospect. Well, it's very good that so far we understand the neutrino oscillation parameters rather well. But unfortunately, we do not understand everything. As I said, we do not know if nu3 is the heaviest or the lightest. Furthermore, we do not know if CP is violated in the neutrino sector. Furthermore, since oscillation studies can only tell us the neutrino mass square difference, we do not know very well about the neutrino, absolute neutrino mass. Also, there are some data that suggest that the oscillation beyond the three-flavor framework. Namely, there are some suggestions of sterile neutrinos. So we have to study more. Finally, it is clear that neutrinos are special particles, and therefore maybe neutrinos are Majorana particles. But, well, we have to test experimentally. Now, well, I think these are the agenda for the future neutrino experiments. But from now on, I want to talk about the CP violation. But of course, we'd like to confirm that CP is violated in the neutrino sector. And in particular, CP violation in the neutrino sector might be the key to understand the baryon asymmetry of the universe, or leptogenesis. So we think CP violation in the neutrino sector might be very important. So we'd like to observe if oscillation of neutrinos and those of antineutrinos are different. However, in order to answer this question, we find that the present generation experiments are not powerful enough. So we need the next generation long baseline experiments with much higher performance neutrino detectors. And in fact, there are two projects going on. One is DUNE, located in United States. Another is Hyperkamiokande, located in Japan. Of course, there are some other possibilities, but for the moment, we'd like to stick to these two possibilities. Now, both experiments are in the construction phase, and until now, there have been various studies on the sensitivity to the CP violation. And the results of these sensitivity studies are shown here. And you can see that both experiments have very good sensitivities to the CP violation. For example, in the most preferred value of the CP phase, about 8 sigma effect should be observed. So clearly, we'd like to see the results from these experiments in the near future. Now, before finishing this talk, I just want to mention the water Cherenkov detectors. Well, the first generation experiments were Kamiokande and IMB experiments, and these experiments observed neutrinos from supernova 1987A, atmospheric neutrino deficit. Also, Kamiokande observed solar neutrinos. The second generation experiment is Super Kamiokande, and Super Kamiokande observed atmospheric neutrino oscillations, also contributed to the solar neutrino oscillation. And Super Kamiokande has been used as the far detector for K2K and T2K. So clearly, the first generation and second generation water Cherenkov experiments contributed significantly to the neutrino physics and astrophysics. So I think it's natural to expect something very important results from hyper-K. In fact, hyper-K is a much larger version of the present super-K detector. The fiducial mass will be about 8 times larger. And because of this large mass, we expect many important research topics in neutrino physics and astrophysics. The construction is already started several years ago, and the experiment will start in 2027. Of course, hypercamiocande collaboration is an international collaboration. Oh, I think I was wrong. We have about 500 members from 21 countries. And the collaboration is growing rather rapidly. Okay, let me summarize. Neutrinos have been playing very important roles in understanding the laws of nature, in particular the laws at the smallest scales. Recent discovery and studies of neutrino oscillations and the small neutrino mass will be very important to understand physics beyond the standard model of particle physics. Neutrinos with smaller mass might also be the key to understand the big question in the largest scale, namely the universe. The question is, why only matter particles exist at the present universe? So I think neutrinos are likely to continue playing very important roles in understanding the smallest and the largest scales. Okay, that's all from me. Thank you very much for your kind attention.
Thanks so much, Professor Takaaki, for this outstanding and so clear lecture and so complete from the starting, discoveries and the prospect and the future. So we are very impressed. We ask now participants if they have questions, comments to address to Professor KAJITA. Please raise your hands and then we will proceed. So if there are questions and comments, I allow always first. So Uri, please.
Hello, thank you for the talk, very interesting talk. I have just a question about the sterile neutrino. You passed a bit quickly from the sterile neutrinos. There are many, different opposite ideas about the existence of sterile neutrinos or not existence of sterile neutrinos. What is, can you a bit explain how you really think that, is there any really evidence for sterile neutrino or against the sterile neutrinos?
Thank you very much for this question. Well, it is true that there are some hints in various experiments, but also there are some data that do not agree with the other experiments. So in my opinion, it is too early to conclude anything. And I think we need a very high sensitivity, very decisive experiment. And until that, I don't want to have any conclusion.
Okay, thank you.
Thank you. So we have a second question or comment. Please, Scott, address your point.
Thank you. Thank you very much for this talk. My question concerns one of your first slides, where you presented on the same slide the first data from 1985. And then on the top of the slide, you had another baseline for the theoretical expectation. And what my question concerns, your error bar on the theoretical side increases with time. And so I was wondering if you could explain the reason why theoretical expectation became less precise over 30 years or so.
Excuse me. One of the first slides. Is it?
Yes.
This one?
That's the
No?
one. Yes.
Yes.
This one?
Yes.
Yes.
Okay, thank you. In fact, the horizontal axis is the solar neutrino energy. Well, the lowest energy one is the PP solar neutrinos, and there's a constraint by the luminosity of the sun. Therefore, the solar neutrino flux is very precise. However, in the highest energy, this is the boron-H solar neutrinos, and the fraction of the boron-H neutrinos are very small. Therefore, this depends very much on the detail of the theory. So the theoretical error is large.
I see. I read the slide wrong. I thought this was a timeline. In fact, it's an energy line.
No.
So
No.
yes, sorry about that. Thank you.
No. Anyway, more questions or comments? So if not, I have I would like to comment, or I mean to add about the absolute mass of the measurement of absolute mass, and because till now we don't have, I mean, the each mass for the neutrino. So I know there is Catherine experiment in Karlsruhe, and are other experiments searching for that, because I found this very important. And then after I will ask, so please this first, and then have another question. So I go, if you could comment on this, please.
Yeah, thank you. In fact, yes, the measurement of the absolute mass is very important. And well, so therefore, I'm really looking forward to seeing the Catherine experiment results. In addition, in my opinion, the data, well, the constraint from the precise cosmology is very important. They already give us a very rather stringent limit on the sum of the neutrino mass. So, well, I think we have to continue the studies of the absolute neutrino mass, and I really hope in some day we have some confidence about the absolute neutrino mass.
Yes, I mean, it appears that it will be there is room for real discoveries in this domain. Yeah. I mean, and that is what is very, very important. I mean, because neutrinos are not hypothetical particles. And the other, absolutely, the other point is about other states, I mean, for neutrinos, for instance, sterile neutrinos, which are very appealing because, in particular, in this school, it has been investigated because it appears very important, neutrinos of such a kind for, in the scale of masses of kilo-electron volt, very important as possible candidates of dark matter, for instance. The important thing is the mass and the statistics. I mean, it needs to be a fermion and a mass in the kilo-electron volt. Yes. And then, Bruno Pontecorvo, who coined the name sterile neutrinos, at least he told me that because was one of the founders of this school together with Chandrasekhar in the early 90s, who inaugurated the school, and have this idea of possibilities of sterile neutrinos. And this summer, and the Batson experiment, I mean, you know that there are recurrent measurements in the so-called neutrino anomaly, the bats, which is there, it appears, I mean, there is the last physical review letters, I mean, this year, which is there, and there are no explanation other that, again, with the neutrino oscillation into other states, not known, for instance. All this call, of course, for extension of the standard model of particle physics, but it's a rather, neutrinos are a rather standard or already part in the standard model of particle physics. So you already comment on this, but I think it's important in both experimental and theoretical. All these neutrino mixing matrices, I mean, and is theoretical and experimental, the understanding, a more deeper understanding of neutrino physics. So neutrino new states, and if new states are there, sterile neutrinos have a room in astrophysics. I mean, are not just saying very abstract. I mean, and that is what I wanted to comment on that.
Thank you.
I have a question.
Yes, we have Jean-Pierre, please address your question to Professor Takaaki.
Thank you, Professor. About the neutrino mass, absolute mass, isn't it hopeless to look for this mass? Maybe we don't have the right instrument now, because the mass is maybe so weak, it's not in our hands to do that. What do you think? Thank you.
Oh, thank you. Certainly, neutrino mass is very small, therefore it's very difficult. Well, but on the other hand, the precise cosmology is, well, I don't know the detail, but rather is the results from the precise cosmology is rather encouraging.
Yeah.
So I'm looking forward to seeing the future results.
Yeah.
Let's hope.
Yeah, from cosmology and large CMB combined with large scale structure, and that is very precise. We have anyway, you know, we have also the problem of which value now for the Hubble constant, and so that also influenciating in the precision, but in any case, it's very important. So, are there more questions or comments? I have, in the tradition of this school, as you know, we have in the name of the school has its own medal, and in the tradition of this school to our distinguished lecturers, in particular Nobel Prizes, we have also Nobel Prize lecturers who came to the school and were from the beginning along the school, and when they were not Nobel Prizes, but they got the school medal. We have the Daniel, in exclusivity, the Daniel Chalonge medal that is real, here I have real, and in exclusivity, and is coined by the French Mint, the French Mint, Maison de la Monnaie de Paris. It has a rich history, and we have in exclusivity the second edition. And we have also in exclusivity from 2015 the Ecole de Vega medal, who is also in all the is posted. And these medals we offer and we award. It's a surprise award, and I want to even virtually, but we hope we have occasion to present to you, or at least to send to you by post, the two medals. So the Daniel Chalonge medal and the Ecole de Vega medal. Chandrasekhar, Bruno Pontecorvo, and then George Smoot, John Matter, Brian Schmidt, Adam Rees, and several others. I mean, Professor McDonald, and I mean other Nobel laureates who joined last year here had received the medal, and it's my honor and my pleasure to make you awarded of our two medals, who also reflect the 30 years of this scientific and human adventure, which is our school, and which you so well presented in the framework in your subject of neutrino oscillations. I mean, and all the problems who crossed this and will cross, because there are problems to solve, fortunately. Unfortunately, more Nobel Prizes for this subject, which is very rich. And we wish also a second Nobel Prize for your researches, including the gravitational wave researches you are doing. So thank you very much.
Thank you very much. It's really an honor to receive these things. Thank you very much.
Yes. You have the two medals. So
Thank
it's
you. Thank you, Professor. Thank you.
Our pleasure, our great pleasure to have received today, in despite of the big delay. I mean, it's late for you. So if no more questions or comments, I would like to thank all of you, and in particular you, Professor Takaaki KAJITA, and then we continue our series. I mean, this month, 23 November, we have our next session. And meanwhile, we continue to keep working in all this fruitful line of research. This school have also the tradition to have open, for instance, the what is today called the a standard model of the universe at the time in the early 90s. There was not even discovered the cosmic microwave anisotropies. John Matter, George Smoot presented in our school the first COVID result, and even before that, the COVID mission, I mean, the project. And so this, in cosmology, there was also in the early universe and the formation of galaxies, it was not so clear avenues in which the right data will came. But this school always put together the most exigent theoretical grounds and the most exigent experimental and observer people with the physics always in the top. Physics always guided this school, and we are very, for instance, and I finish with that because I see there are many people who, do not know that. For instance, dark energy, when it was discovered in the late 90s, most of our colleagues, our astronomers and astrophysicists did not accept it and keep on saying are a systematic zero, because acceleration of the universe, how the universe was expanding but without any acceleration, and how that is possible. The interpretation of the team, Brian Schmidt and Adam Rees, it was really very outstanding, very novel. And we, from the beginning, we take and said, this is the vacuum, this is the cosmological constant, which, by the way, today is not more constant. We are exploring, all that, because it's a rate. It's the way as the Hubble constant. The Hubble constant is not a constant, it's a Hubble rate. And we measure today, and so it's not so in the early universe. And so this is our most enthusiasm and satisfaction that we keep in the lines of research. We were successful because of the physical and the cross of the theoretical physics with experiment and real data. And if the models are not fitting the data, are not agreeing with the data, even if they are very beautiful and very elegant, we need to make confrontation and disregard those models which are not reproduced in nature. And that is one of our, satisfaction.
Yeah. Thank you. Very good.
That is why you are here, and that you are here with all this data and new perspective and real physics and rich physics and astrophysics. Thank you very much. Thank you to all of you. So I said goodbye now.
Thank you. Thank you very much. Bye-bye.
Bye-bye. Thank you. Bonjour, Pierre Rocus. So